a Limacon has the form, Limacon. So it has two different forms. R equals A plus or minus B cosine theta, or R equals A plus or minus B, it could be sine theta instead of cosine, where A and B are constants. So we're talking about graphing functions, R as a function of theta. That's what we're really talking about here. Either way, you can think of it as R as a function of theta. So it's different than what you're used to. There are 4 kinds of Limacons. The good news is your calculator will graph these for you, but you might have some crazy teacher that doesn't let you use your calculator. So I'll show you the way I had to learn this, and then I'll show you on the calculator, you can use that to remember it for you if you need to. The graphs I'm about to show you are, if I remember right, I used to have all this memorized, for something like A minus B sine theta. But if you change it to A plus B sine theta or change it to cosine, the graph will be rotated. And I'll say more about that as we go. So if it turns out that the absolute value of this number divided by this number is a proper fraction between 0 and 1, then you get a graph that has an inner loop in it. So it'll look, I haven't drawn from this perspective yet. Okay, so don't laugh at me. This is not going to look good. It'll look kind of like that. Kind of like a heart. But with an inner loop. With an inner loop, though. And then it'll be nice and smooth down here.
Is it an apple?
Kind of looks like an apple. But as that absolute value of A divided by B, as that increases, the loop shrinks down. Eventually, it just becomes a cusp. And so this is called an inner loop Limacon, this first one. But if A divided by B gets bigger and it turns out to be exactly 1, if the absolute value of it is exactly 1, you actually do get a heart shape. It's called a cardioid. And so you'd get something that looks, again, don't laugh at my graph. Drawing it freehand is not easy. You get something that looks like that. And it could be upside down. It could be rotated 90 degrees one way or the other. All right. Now, what happens if the absolute value of A divided by B gets even bigger and is between 1 and 2? Then the cusp flattens out to a dimple, and it looks like a lima bean. Oh, so maybe that's why we call them Limacons, right? So, or maybe that's why, well, it's the same root word anyway. So it's based on food. No, it just has the same root word. It does look like a lima bean. So it wouldn't flatten out, but it would get like a little dimple instead of a cusp. And it would be very smooth. Ah, darn it.
That's pretty smooth.
What is your problem, you guys? I don't know what you're imagining, but get your mind out of the gutter. All right. And then if the absolute value of A divided by B gets bigger than 2, that dimple just flattens out and it becomes closer and closer to a circle as the absolute value of A divided by B increases. So it might be a little bit, depending on how big it is, it might be a little bit flat. And then it starts really looking like a circle. But it will flatten out, at least on one part of the graph. I drew it on top, but again, it could be rotated. So we're going to graph 1 plus 2 cosine of theta. All right, what is A, what is B? A is 1. So absolute value of A divided by, I can't talk. The absolute value of A divided by B is 1 over, what's B? 2. So you get 1/2. So which of the above graphs do you expect to get? Inner loop. You expect it to have an inner loop. So that's helpful if you're not allowed to use a calculator to graph this thing. if you know ahead of time that has an inner loop. Otherwise, it doesn't matter. If you're allowed to use a calculator, you don't need to remember that. And you are in this class, but I don't know what's going to happen in your other classes, so I got to be careful. All right, so let's plot a few points. This will be helpful in understanding polar coordinates. So here are the points I recommend plotting. Now, you actually plot theta values because it's r as a function of theta, so you'd want to input theta values because r is by itself, right? Just like if you have y as a function of x, you input x values. So what would good theta values be to input? Well, theta values at the corners, do you know what I mean by that? Yeah. They're not really corners, but like on the axes, if we were looking at x and y axes. So like 0, 90 degrees would be pi over 2. I'm going to leave a little space there. Pi over 2. Well, what about pi? Pi, 3 pi over 2, and then back to 2 pi. So remember, the corners then would be, let me make this graph paper bigger. So the corners would be 0, 90 degrees would be pi halves, pi, 3 pi over 2. And then 2 pi would coincide with 0. One thing I should mention, though, is that if I go back up here just for a minute, if it has cosine in it, it'll be symmetric to the polar axis, which coincides with the positive x-axis. So if it's cosine, it's symmetric to the, we'll just say the x-axis, polar axis. And if it's sine, instead of cosine, it's going to be symmetric to theta equals pi over 2, which is the y-axis. So symmetric to the y-axis. And that's handy to know, because if it's symmetric to the x-axis, the top half of the graph will be the mirror image of the bottom half. And if it's symmetric to the y-axis, the left half of the graph will be the mirror image of the right half, and vice versa. So that's nice to know ahead of time. Okay, so you can count on this guy being symmetric to which axis? Since it's cosine? The x-axis. All right, let's plot these points and keep that in mind. So once again, you look in the direction of 0 radians, and then, plug in 0. What do you get? For what's the cosine of 0? 1 times 2. 2 plus 1? 3. So we can look in the direction of 3 of 0, actually, and then go out 3. 1, 2, 3. Actually, let me just finish plotting these, and then we'll plot all. Then we'll actually graph the points. So pi over 2, what's the cosine of pi over 2? 0. Times 2 is 0, plus 1 is 1. Everybody buy that? Okay. Pi. What's the cosine of pi? So you plug in pi. What's the cosine of pi? Cosine of pi. Negative 1. Times 2 is negative 2. Plus 1 is negative 1. Everybody see that? Okay, 3 pi over 2 cosine. 0 times 2 is 0, plus 1 is 1. Cosine of 0 is 1, but if you multiply that times 2 and then add 1, you get 3. Right? So I'm just doing arithmetic. Okay, 2 pi. What's the cosine of 2 pi? Oh, same as the cosine of 0, so you're going to get 3 there as well. So all I'm doing is plugging in those points. Does everybody see what I did? If you have trouble with that, technically you're supposed to have the cosine of those values memorized, right? But if you don't, you have your calculator to help you out. At least in this class. What's going to happen in your next class? I don't know. So if we plot 3, 0, you really think about, it's probably easier to think about the theta first. Look in the direction of 0 radians, and then go out 1, 2, 3, there it is. Look in the direction of pi over 2, straight up, and then go out 1. There it is. Look in the direction of pi. So we're looking at this point right here, you guys. And then, you go negative 1. So you look in the direction of pi, but you go negative 1. So which way you're going? Right here, right? Look in the direction of 3 pi over 2 straight down, and then go out 1 right here. And then you get another copy of this point, 3. If you look in the direction of 2 pi, go out 3, right there. So maybe that's not quite enough points to get an idea of how wide this thing gets. I will give you one other point you get for free. It's going to go through the pole, which is the origin. So we didn't plot it, but it'll always go through, an inner loop Limacon will always go through the pole. Now there's another point we could plot, maybe in the first quadrant, something convenient. Can you think of a value where you take the cosine of it, you get something nice to work with? Pi over 4, you get rad 2 over 2, not as nice to work with if you're graphing. Pi over 6, you get rad 3 over 2. How about pi over 3? How about pi over 3? So what's the cosine of pi? So the idea, guys, is you plug in pi thirds. What's the cosine of pi thirds? 1/2. And then you multiply that times 2. 1 plus 1, 2. So if you look in the direction of the spoke that's at an angle of pi thirds and go out 2, 1, 2, there you are. It gives you an idea, at least, of something to shoot for. Okay, now remember, it's an inner loop Limacon, so let me show you how to draw that. You would start maybe here. I don't know how wide it gets, but eventually it's going to swing down to that value, right? And then it'll actually go into the second quadrant, not very far, and then swing around and create the loop like so. And then it'll go back through the origin. Remember, the bottom half is symmetric to the top half, so I'm just copying what I did above. This point will get reflected down here. So I get that point for free using symmetry. And I just make the bottom half look like the top half. Boom. Close enough. If I want a more accurate graph, I plot more points. Calculator. Most of you will probably want to check your answer on the calculator. I'll just tell you where it is. We're going to run out of time if I show you everything now. So if you go to, so if you're here on the home screen, go to mode. And then it's probably a good idea to make sure you're in radian mode. And then go down to the one that says function. I think it's the 5th one down. Well, and then change arrow over to polar. Yeah, polar mode. And then if you go to y equals, I guess I can graph it real quick for you. What was it? 1 plus 2 cosine theta? Hit zoom number 6. And you could zoom in a little bit if you want. Go zoom. Maybe get the cursor kind of in the middle. There it is. It looks a little more elongated, but that's because of the scaling on the graph. If you go to zoom square, number 5, it'll look more like what I have. So my graph isn't too awful. It's a little more rounded right here in reality, I guess. But if you're doing it by hand, that's fine.